Okay, now it's now recording. So good morning, everybody. Bom dia a todos. We are going to start the class 10 of Reservoir Simulation. So I hope the seminars were clear for you and you could understand the main activities that we have in Reservoir Simulation. And now we are going to start a new part of the class. I'll try to use these last classes in the second part of the course to show you some aspects that are inside the reservoir simulation. So for those who are not familiar with that, I'm trying to give you some hints and how the simulation works and how we need to use them in our practical applications that we have seen in the first part of the course. Okay. So first of all, in the other classes, I saw that you didn't ask any questions. Please feel free to ask any questions, any doubt that you have, any comments, any experience you have in the projects or in your real life before the PhD or the master. Feel free to ask questions and talk at any time. Okay. I'll try to see the chat here, but if I don't see, Danielle, please help me just saying that we have questions in the chat, okay? Okay, so let's start. Today, we're gonna go until 15 minutes before 11, because I have to stop that. So we're gonna have a very short break in the middle, okay? So the idea here is to repeat a little bit what we have seen in the first class, not the closed loop, because the closed loop I hope you have understand, but if you have questions about the closed loop, you can ask again. Now I'm going to talk about the introduction and some general aspects of simulation. And I'll go very briefly to an application of the closed loop just for you to ask questions about the project and just to see if you are okay with the projects. So reservoir simulation, as you have seen, as you noticed, is a tool that's widely used in the industry. The main activities we do with reservoir simulation is the forecast production. Because this is a very important aspect for the company. The oil is an asset of the company, so it's very important for the engineers to have a very precise production forecast, because this is the money of the company. Okay. Other than that, we also use reservoir simulation in the decision analysis process. So we want to develop the field, we want to manage the field. So this is the main activity of reservoir engineering, using the reservoir simulation to do that. In order to do that, we have to go through this closed loop in all the applications you have seen in the classes so far. Okay. We also use reservoir simulation in complex studies, because real life reservoirs, we have faults, fractures, bugs, as Manuel has shown in the integration of geology and geophysics. We have seen that the reservoirs are very complex. So we have several tools to forecast production. We can forecast production even with data only, but reservoir simulations are the most reliable technique that we have. So we are going to see in the next class today, in the next class, some basic aspects of the reservoir simulation. And as you will notice, the models have a lot of problems and a lot of limitations, as we have. As I'm writing here. But despite of these limitations, the reservoir simulation is today the most used and most reliable technique that we have for forecast production and decision analysis. Okay. So when we want to study complex reservoirs, complex process like water injection, steam injection, polymer injections, and so on, these tools are the best way we have to forecast production and to make decisions. I'm going to emphasize in the next classes and today in next class these limitations, because it's very important for you if you're going to use reservoir simulations in your real life after your graduate studies. it's very important for those who use reservoir simulations to understand their limitations. So I'm trying to emphasize the limitations in this course, because I think it's more important for us to understand the limitations, so we understand how much we can use the tools, than to just use simulation. Because I have seen in my life a lot of people in the industry, just even students, just using simulation and thinking that the result of a simulation is the real truth. And that's not true, right? Models are models. They have errors, and they have a lot of errors, and our models have a lot of errors and uncertainties and so on. And it's very important for us to understand that, in order to understand that our production forecasts have uncertainties, have risk, have opportunities. And also it's very important for us to understand that in order to make decision analysis, we are going to use models in the closed loop process, as we have seen, but we have to consider the errors and uncertainties, okay? So I'm going to emphasize a lot the errors at a point that maybe some of the students will think, well, if the simulations have so many errors and so many uncertainties and so many problems, why we use these simulations? We use these simulations and we use these models because it's the best tool we have so far. And because in the closed loop, I hope you have shown you, as we have data and have dynamic data, we can adapt the models and we can improve the quality of the models, and we take better decisions as we go in the process, okay? Okay, well, which are the main limitations? First of all, is the numerical errors, right? Numerical models have errors in engineering, but reservoir simulations have much more errors than traditional other areas of engineering. We're going to talk about that today and then next week. But the main problem with reservoir simulations is that we are trying to mimic a physical behavior that is a flow of a complex fluid in porous media. And the porous media, as you know, have a scale that is very small. And we have to do that using reservoir simulation blocks of sometimes 200 meters or 100 meters or 50 meters. And in the vertical direction, maybe 10 meters, 5 or something like that. So the discretization in our area is very different from discretization in other areas of engineering. So our errors are much bigger than the errors that we find in the other areas of engineering, okay? So this is one of the main limitations we have. And why we use these so big blocks? Because of the limitations in computers, right? We have limitations in memory, you have limitations in time. If you want to simulate a reservoir like the ones we have in Brazil in the pre-salt with a billion blocks to have a scale that's okay for us to mitigate these problems, we're gonna wait. We have to have very powerful machines with a lot of memory, and we have gonna wait months to finish the simulation. So that's not a viable technique. So I'm gonna talk a lot about these errors, and we have to be very aware that these errors have problems. The main problem of these errors is not only the errors, but also the bias that they bring to the results. Okay, I'm gonna talk about that briefly today and next week. What is the bias we have here? For example, if I have blocks of 100 meters or 50 meters, we're gonna have a numerical dispersion, for example, that the water, instead of from the injector to the producer, instead of getting there in 6 months, we're gonna get there in 2 months or in 1 year. So the error can be very big if we consider discretization errors. That's why the data assimilation in history matching process is very important. And that's why it's very important for us to understand that we have these errors and we can use some techniques, upscaling techniques and so on, to mitigate these problems, okay? But this is one of the main limitations we have in our models, and we have to very aware of that. Okay, the other problems we have with these models is that we have a lot of uncertainties. We have uncertainties in several processes in engineering, but in petroleum management, petroleum reservoir management, this is very important. Why? Because we have a very information in wells. Each well is 1 kilometer or more from each other, especially in the offshore fields in Brazil, where we don't have many wells. It's different, for example, when we have 100 wells in a field that's very small or something like this, an onshore field, maybe a little bit different. But for us, in Brazil, at least with the pre-salt fields and campus basin fields, we don't have many wells, and the seismic is very limited in the resolution. We have seismic 4D, but not for the old reservoirs and so on. So we have a lot of uncertainties in the process. And it's very important to understand how to deal with these uncertainties, how to manage these uncertainties, how we mitigate the problems that are related to these uncertainties, or how we use these uncertainties in our favor, okay? So we, Manuel and Célio and Alessandra, probably they talk a lot about this, and it's how to mitigate these problems. So that's why we invert a little bit, we give the seminars before. So when I talk about this, maybe you understand a little bit what I'm talking about, okay? But if you have any questions, again, please let me know. The other problems that we have is that we have to represent the fluids. The petroleum fluids are very complex. We have several components. We have CO2 mixed, we have water, we have a lot of components, different components in this thing. But if we want to represent all these components in a compositional model, as we're going to see in this model, we're also going to wait a long time for simulations to go. So normally we do some simplifications in the physical process. We're going to see an example of a model that's called black oil. Probably you heard about this, where we try to represent the petroleum only in two components, a light component and a heavy component. And the light component more or less represents the free gas and the gas, and the heavy component represents the liquid. And then we have water, so we have just three components. And this black oil model is much faster than the one that we try to represent several components. And we try to use these models in some aspects of the reservoir simulation just to speed up the process, okay? But even if you use compositional model with 6 components, 7, 10 components, it's still a simplification of the fluid. So the fluid is very complex, and the physical recovery process is very complex, and we try to simplify that in order to speed up the process, okay? And the last one that I'm gonna mention, that these are not the only 4 limitations, but these are the main limitations we have in our problems, okay? Is the well modeling. We are gonna see that the well is a very important part of the reservoir simulation models. Why? Because in the wells is the place that we are gonna measure production and measure the injections and so on. So sometimes we have a very good models. We spend a lot of money acquiring information about geology, geophysics. We are representing the reservoir in billions of blocks. But if I have a well model that's not good, then I'm at the end, the production forecast will be wrong. So I'm going to talk a lot about well modeling, because this is very important. And João already talked a little bit about this and the integration of production facilities. So it's important not only to have good well models, but also to integrate with production facilities, because here we have good boundary conditions, okay? So these are the 4 limitations. We're going to talk about these limitations as we explain what's inside a reservoir simulation model. And please let me know if you have questions about them. And also, we are going to try to talk about these limitations and talk about how we can manage to have good models despite of these limitations, okay? Any questions? Okay, so if you don't have any questions, well, the idea is now to do a very brief presentation about simulation, and then we are gonna cover a little bit about what's inside the simulator. Okay. So reservoir simulation is not more than a computer program that tries to solve flow equations of mass and sometimes heat in porous medias. And we have also boundary conditions that are trying to impose the fluid movements to the reservoir. So initially the reservoir is, the fluid is there, it's not moving. So when we place wells, producers and injectors, we're gonna change the boundary conditions in some place of the reservoir. For example, in the injectors, we're gonna increase the pressure, and this pressure will try to dislocate the oil to move the oil into the producer. So the producer is the opposite. We are going to decrease the pressures in some place of the reservoir where the producers are, and this difference in pressure will move the oil into the producer. So we are going to cause an instability by placing the wells in the reservoir, and this will change the boundary conditions, and then we are going to cause this movement. And what we have to do in the reservoir simulation models is try to model this movement using some physical aspects of this behavior. Okay, so it's very important for us first to construct these models first to understand the physical behavior or what's causing these movements. Then we are gonna try to understand this behavior and write mathematical equations in order to mimic this physical behavior. We could solve these mathematical equations, but as we have a complex reservoir with complex boundary conditions and complex fluids and so on, instead of solving the mathematical equations directly or analytically, we normally solve them by a numerical method. So we discretize the reservoir in blocks, and we try to write the mass balance equations from block to block and try to use numerical techniques to do this. Once we have these numerical techniques, we write the computer programs, and then we have a tool like IMAX that we are using to simulate the flow in the mass flow in the porous media. Sometimes the heat. We are not talking a lot about one of the simulations that we have here, which is the thermal simulator. In several places of the world, the thermal simulations are important because we have difference in temperature. For example, when we are injecting a fluid that's hotter, like that inject of or changing the temperature of the reservoir and so on. We are not talking a lot about this thermal simulator here in our course because the thermal simulator is not very used in Brazil because the focus of Brazil is really the pre-salt, and the pre-salt normally we don't use thermal simulators. Okay, so I'm gonna mention the thermal simulators, but we're not talking about the equations. So we don't have to use this difference in temperature in our equations. We're gonna assume that although we have a difference in temperature in the fluid that we are injecting and fluid, the difference in temperature is not big enough to influence our equations. Okay. And the main targets is what we have seen in the last slide, which is the forecast of reservoir production here, and decision analysis in order to maximize objective functions. For example, final recovery, the profits, mitigate risk, and so on. Okay. Okay. So reservoir model is a representation of the real model, and through a discretization of space and time. So we are going to discretize not only the space in blocks, but also time. We're going to advance in time by time steps. So we're going to initiate our process when the wells are producing an injector, and then we're going to simulate from time step, try to mimic the behavior of the reservoir and try to understand this flow through porous media in time. Okay. So we are going to have this physical modeling, mathematical fluids in porous media, which is the ones probably you're taking reservoir engineering classes, or you did it before, so we are going to use the same equations that they are using. So, but we are not spending too much time in the equation. I'm here and just not explaining too much equations. I'm just trying to explain you how we're going to use the equations in the simulator. Okay, we're going to have boundary conditions in all, because this is important for our numerical models. We're going to talk about the different type of boundary conditions we have. For example, we can have an aquifer, we can have a closed reservoir, we can have a well. All these are considered for our numerical model a boundary conditions, where we're going to have conditions that we're going to have difference in pressures or difference in rates. And I'm going to explain in detail how we impose these boundary conditions for the reservoirs. Okay. So we are going to, the number of equations we're going to use and solve is a function of the complexity of the reservoir. So if you have a very complex reservoir with faults and bugs and so on, and very complex geology, we are going to try to represent the well in a finer model, blocks, smaller blocks, and so on. So also, the fluid is very important for us to understand. The fluid and the recovery process together are important for us to select how we're going to discretize the reservoir. So I'm going to give you some hints, probably not today, in the next class, on how to select the grids. This is one of the choices the reservoir engineer have to do. I'm going to simulate the well, the reservoir with 100 blocks, or 1,000 blocks, or 100,000 blocks, or 1 billion blocks. This is a function of how good will be the representation of the geology, of the fluid, and of the recovery process, and how much time we have and how much money we have to simulate that. So we have to select a combination of the best representation of the reservoir fluid and the recovery process, and the amount of time and money and computer that we have. Okay, this is very important, and this is a very important aspect of our problem. That's why in the closed loop, I don't know if you remember, we call the final models that we are going to use the fit for purpose models, right? Why fit for purpose? Fit for purpose is a name that try to represent this relationship between the quality of the model and the time we need to simulate the model. Okay, so we have to spend a lot of time in the steps 2 of the 12 steps that we have seen, as Guilherme Avanci told you, in order to try to improve the quality of the model and reduce the computational time. Sometimes we don't spend too much time there, but it's very important for the reservoir engineers to spend a lot of time in this step 2 of the closed loop. Just to give you an example, last week, the past weeks, we are simulating a real field from a shell, and the simulation model was running in 9 hours. And our team, that Célio, Avanci, and so on, could reduce the simulation time and almost 10 times, keeping the same quality of the results. So imagine that we are going to optimize production, we're going to do data simulation, as you have seen in the seminars and so on, and we're going to spend thousands of simulations. So instead of running in 9 hours, we are running in 1 hour. That makes a very big difference, right? And the result is almost the same. So that's very important for us to understand what's inside the reservoir simulation in order to be able to do this calibration. Okay. And what does make a difference in our models from other engineering areas? As I have told you in the last slide, the physical problem with uncertainty that we have, the scale that we have, as I have told you, we are trying to emulate a physical process that occurs in the porous media, but we are using blocks of 100 meters. So that makes it very, very different from other engineering areas. Sometimes people that are used to do numerical techniques in other areas and come to reservoir simulation area, and I don't believe that the difference in the scale of the process and the scale we are using to model the process. So is this a problem? Yeah, it is a problem. But if we are aware of this and we use some techniques to reduce this problem, we can use these numerical models to, with a good accuracy, to take decisions, okay? The fluid also, as we have seen, the fluid is very complex. The well limitations that we have. And in order to speed up the process, we have to do a lot of simplifications. And so our model is a physical emulator of the problem. And we have errors, we have problems. And it's very important for you when you finish this reservoir simulation class that you understand that we have these problems, and there are ways to overcome these problems and improve the quality of the models, and we still are able to use this model to forecast production and to take decisions and so on. Okay. Okay. Now I'm gonna go a little bit fast because we have seen a little bit of this in the seminars and in the first class I gave you. I'm just doing a review of the process, but as I'm going fast, please interrupt at any time if you have any questions or doubt about that, okay? So what we're gonna do to construct reservoir simulation models. Here's an example of a model of a real reservoir. We have here the blocks emulating the size of the block of the simulation. For example, here we can have blocks of 100 or 50 meters, or sometimes even 200 meters, and in the vertical directions a little bit less. I'm going to explain why we use this vertical. The resolution in the vertical directions is much lower than the horizontal. This is another problem of reservoir simulation models. Sometimes people from other areas say, okay, if you have kilometers in this direction and we have meters in this direction, why you don't use a 2D model? That could make sense for other areas, but for us, we don't use a 2D model. Even if you have meters here and kilometers here, it's very important for us to discretize the vertical direction a lot more than the horizontal direction, because this movement of fluid in the vertical direction is very important. For example, when we have an aquifer and the water is going up, for example, when we have an injector and the gas is moving in the vertical direction, or the water is moving. When we have, for example, water cutting, as probably you have seen in the reservoir engineering classes, or gas cutting, that's the gas going back and so on. So the vertical movement of fluids is very important for us to capture the behavior of the wells, okay? Sometimes we have horizontal wells here. For example, if I have a horizontal well and we are producing from the bottom part of the reservoir, is also another example why we need to discretize this and so on. So we have several reasons for doing that. That may be sometimes it's strange for people that are not used to this reservoir simulation, because if you have only like 100 meters here and kilometers here, would make more sense to have a 2D models, but we use a 3D models in order to capture this fluid movement in the vertical direction. That for us is very important, okay? And if you have questions, just stop me. So what we are gonna do, we are gonna discretize this reservoir simulation model, and each block of this will represent an equation. I'm gonna show the equation of the conservation of mass in one of the blocks here, and we're going to apply this conservation of mass for all the blocks in the reservoir simulation model. For example, if you have 1 billion blocks, we have to solve at least 1 billion equations. But as we have to solve for water, for each component of the gas, for example, if it's a black oil model with 3 components, each block we're going to have 3 equations to solve and 3 unknowns to find. So we're going to have 3 billion equations if you have 1 billion blocks. So if we're going to 1 million blocks, 3 million equations, and so on. Of course, there are ways to decrease a little bit the number of equations we have, and so on. I'm going to show some hints about this. But basically, if you have 1 million blocks, we're going to have 1 million equations to solve. 3 million goes to solve. Okay. It's the most common reservoir simulation model is like this. I'm going to show a little bit of variations in this, but this is a general idea. And here in the bottom part, I'm trying to show just an example. This is not a really reservoir, but it represents more or less what happens in a porous media. So imagine that we have a well here, we're going to produce here, an injector here, we're going to inject water, we're going to try to change, move this oil into the producer and so on, and look at the complexity of this geology here. And sometimes my simulation block is like this, right? Or like this. For example, I have an injector here, I have a producer here, and I have to simulate this. So we have to do a lot of simplification in order to simulate that. But at the end, we have to try to write the conservation of mass equations for each block. We have to go see the mass going in. We have to see the mass going out, and the accumulation of gas inside. For example, if we have this representation here, each block here, we will try to write the conservation of mass here. We're going to write the conservation mass and see how much mass is going from here to here, then from here to here, then from here to here, and then from here to the producers, okay? So that's the basic idea of the reservoir simulation. We're going to give details about this, right? And first of all, we have to understand the physical behavior, why the fluid is moving. So basically, in our equation, in our basic equations, the fluid is moving because of difference in pressure and gravity. So just take this. So if you have, as I put here, a producer producing here, right, and an injector injecting here, I'm increasing the pressure here, and I'm decreasing the pressure here as I put the producer here and I put the injector here. As I have a gradient in pressure here, the fluid is moving in horizontal direction because I have a higher pressure here and a lower pressure here. So I'm trying to mimic this behavior in each of the blocks of the simulation model here, okay? And also the fluid is moving because of gravity. For example, if I inject water here, and the water is heavier than the oil that's in the reservoir, like in the pre-salt field, for example, the water will not move horizontally. The water will move a little bit horizontal, but also vertically. That's why we need to have a very better representation in the vector direction here, because the water sometimes is moving here vertically. And sometimes we have examples that the water moves vertically here and gets to the producer very fast, and then we leave a lot of oil behind here. That's why we have to improve the quality of the models in the vertical direction in order to have a better recovery factor for the reservoirs, okay? So we have to understand all this, the physical behavior. Then after we understand this physical behavior, we're going to write the mathematical equations that represent these mass balance equations in the block. And that's what we are going to do in the next class for you, okay? In order to do that, it's a multidisciplinary team. You have to understand all these areas, and I'm not going to spend time here explaining you why. Probably at this point of the course, you know, we need to have good models, good geology, good information. We have to write all this information, the reservoir engineering part, the physical behavior of the process, the mathematical equations that represent this physical behavior. We have to understand about the numerical techniques to model this thing. Sometimes we have to understand about a little bit of chemistry and about the fluid behavior, thermodynamics, and so on, computer program to make these models to have faster and so on. So it's a very multidisciplinary team that have to work. Also economy, because everything we do it's important because we want to produce oil to make profits, and it's very important for us to understand this and to make decisions about using these models, okay? Okay, these are the main activities we have so far. I'm not going into details here because you have seen the seminars, how to forecast production, how to optimize production, how to perform data simulation, how to represent different aspects of the reservoir, barriers, bugs, and cars, and geology, and so on. So I'm not spend too much time here because you have seen this in the seminar. So if you go too fast in one of these slides and you would understand, please let me know, okay? So what we are gonna do, give you details about these flow equations in porous media. And what we're gonna write basically is the Darcy's law, as you have seen in reservoir engineering classes. The state equation to represent the fluid behavior. And we're gonna write this, we're gonna put these two aspects in the mass conservation equations that in petroleum we call continuity equations or mass balance. But we are just writing the mass balances as using this concept, the fluid that's going in, the fluid that's going out, and the fluid the mass that's accumulating inside the block, okay? These are the basic equations that we're gonna write. When we do all this, we end up with this, what we call in petroleum engineering, the diffusivity equation, which is not more than these equations that try to represent this physical behavior in the process. Of course, we can solve these equations analytically for very simple problems, like theoretical problems or 1D problems and so on. We can solve this equation analytically, but for complex reservoirs, we have to do and solve them numerically, as we have seen in the previous slides in the seminars, okay? What is a numerical representation? I'm gonna go very fast here because it's not the objective, but what we are gonna do is basically this. If you have a reservoir that's like this, and for example, we have a producer here and an injector here, I'm trying to represent this fluid behavior of the water displacing oil into the producer. I'm gonna write this by putting the reservoir simulation blocks here, and simulation, for example, the mass from here to here, the mass from here to here, from here to here, 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 here. So the mass will be simulated by taking each of these blocks and writing the conservation equation, the mass that's going in, going out, and accumulating in each block. We have also these boundary conditions, as we have seen here. For example, in these examples, it could be a closed reservoir. For example, a closed reservoir is a reservoir that we have no flow through the boundaries. So we have to write this. And of course, we can have an aquifer here, for example. If you have an aquifer here, this part of the boundary equations, instead of being a closed reservoir, is a part that the water is coming into the reservoir if we have pressure in order to do that. For example, initially the aquifer is there and we have equilibrium, so the aquifer is not moving. But if I have a producer here and where the pressure here is decreasing in these aspects, so if I decrease here, the pressure of the aquifer will displace the oil also into the well. So also we can have a boundary condition that's not an aquifer, for example. Or I can have a fault, or I can have a well, and so on. So not only we're going to discretize the model, but also we're going to put the boundary conditions and the initial conditions to simulate that, okay? So again, physical process, equations, we're going to discretize the equations. We are going to linearize these equations in order to solve the problems. We're going to impose the boundary conditions. Here's in Portuguese is condição de contorno, but here's boundary condition and initial conditions, okay? We translated to English, but forgot about this, is boundary conditions and initial conditions. And when we have this, we have a model, and we're going to simulate the process as we have seen in the seminars, as you are using in your projects, okay? In order to do that, we can have a very simple models like a 1D problem, which is basically the mass material balance, as probably you're gonna, you are seeing that in the reservoir engineering classes. When you have a 1D problem, is a material balance, okay? I'm gonna talk about other models, but very briefly, because we don't use these models anymore. It's just for you to understand that sometimes we can build very simple models just to understand physical aspects of the problem. Today, we don't use 1D problems, but sometimes we can write 1D problems as, for example, we are trying to emulate a behavior of well that is here in this complex reservoir, for example. we can pick up this well here, and we want to model this well in detail just to see how is the behavior close to the well. So in order to do that, we can take a very piece of the reservoir here and write a 1D model like this, where we represent the well, and here we have the influx and the boundary conditions here, and we try to emulate this 1D well just to understand. So instead of using 4 blocks here, I can use 100 blocks here just to model very detailed reservoir, just to understand the behavior of the fluid close to well, okay? Not that we're gonna use the 1D models to simulate the whole reservoir, but we can use 1D and 2D models to understand physical behavior in some parts of the reservoir, okay? So we can write this horizontal 2D or vertical 2D models in order to have the same type of behavior. When we want to understand gravity segregation, cross sections, and effects of vertical wells on displacement and so on, we can write these 2D models just to understand these physical aspects. But for real reservoirs, normally we have 3D models like this one. We can have very simple 3D models like these Cartesian blocks here, where we have very regular blocks, which is nowadays not very common anymore. Sometimes we can write these 3D models, but radial models, this is very important. For example, again, when I try to simulate a well, a behavioral well like this one, we can write these radial models here, which are 3D or 2D or 3D. But as we have vertical wells or even horizontal wells, we know that the flow here is radial, is not linear. Instead of having a Cartesian block, for example, or a very regular Cartesian block, we can write these radial models or different type of models to represent the fluid behavior. I'm going to give you some hints about these aspects, how you're going to select the grid. Okay, here just giving you some examples. But for example, if you want to study the gas conning or the water conning or the flow behavior very close to the well and these things, we can write 3D or 2D radial models. Okay. At the end, we're gonna have real models that are like this. Nowadays we have very useful tools in order to write these very complex grids. The complex grids are more important to represent this type of heterogeneity. We have these inclinations we have in the reservoir, these complexities. So as we have Petroleum and RMS software and geology model that are able to build these complex grid models into the reservoir simulation models, many people are using these complex models in order to represent better the boundary conditions, the fluid behavior, and so on. Okay. We're going to talk a little bit about this, probably in 2 classes from today. There are a lot of advantages on using these complex grid models, but also there are some advantages. So I'm going to explain you a little bit about these advantages and disadvantages. But nowadays, the advantages are a little bit more important than the disadvantages. That's why normally the new simulation models we have in the companies are using these complex models. One of the big problems of these complex models is that the blocks are not regular. As they are not regular, we have to understand how to mimic this flow behavior in this complex geometry. Sometimes the blocks are like this, for example. So we have to write the mass conservation from this to this. So there are some physical aspects that are not so easy to model if the blocks are like this, for example. And I write the mass conservation from this to this block. It's much easier to write the mathematical equations than in a complex geometry like this. But nowadays it's possible to do it. They are there in the simulation models, and we are using these models, and we're going to concentrate in the analysis of these complex models. Okay. I'm going to jump to this. Okay. What kind of simulations you have? So what I'm going to talk today in next class. One of the most important things that you are going to do as reservoir simulation engineers is to select which kind of model you are going to use for each type of problems, what we call fit for purpose models, right? The fit for purpose is exactly the meaning of this. I'm have to all the time as reservoir simulations engineers, you're going to have to build the models and use the models, and we have to select the models the best way you can to have the best relationship between the quality of the results and the time. So what here I'm giving you some hints, and the next class I'm going to detail more these hints, and which are the most important aspects for this selection of the models. Okay. Of course, one of the most important is the type of fluid. Why? Because we are trying to mimic the fluid behavior and the fluid flow in the reservoir. So we have to select the fluid that's most compatible with the fluid model that's most compatible to the fluid. Okay. So sometimes we have gas reservoirs and we have just gas and water. Sometimes we have heavy oil models that we call black oil models, where we have a very heavy components and mostly heavy components and water. So maybe we can simulate this as a 2D, as a two-phase models. It is also two-phase model. Sometimes we have a very light oil and light components of the oil. I don't know how much you guys understand at this point about thermodynamics, but we are not going very deep in thermodynamics. But if you have a light oil, for example, and we start changing the pressure, we're going to give you a little bit of hints about that. But if we change the pressure in the reservoir and we have a petroleum that have a lot of components, and some of these components are light and other are heavy, we are going to change the phase in the reservoir. For example, in the initial conditions, the reservoir can be liquid, but as we produce this oil, the liquid can be transformed in gas. So it's very important for us to have a simulator that can mimic this behavior, because the gas movement in the reservoir is very different from the liquid movement. So if we have these conditions, we have to select a model that is able to mimic this behavior. Okay. So independent of if a two-phase gas, water, oil, water, three-phase, black oil model, as we're gonna see, or compositional model of several components and so on, we're gonna write the equations in the simulation models using NP phases. So remember this, because I'm gonna use a lot of these in the equations. So the phases, for example, for black oil models are water, oil, and gas. Okay, so we have these three phases in the reservoir. So if you have three phases in the reservoir, we have just NP equals to 3, right? So we're gonna write 3 equations for trying to mimic this flow behavior. Why 3 equations? Because we have to understand the water movement in the reservoir, the liquid movement in the reservoir, and also the gas movement in the reservoir. So if you have 3 phases, we're gonna have 3 equations to solve for each block, okay? Another important thing here is that we have number of components. So if the petroleum is a mixture of several components, we are going to mimic the behavior. We can mimic the behavior of these components. So we want to understand how these components will move through the reservoir. So again, if you have several components, we're going to have, for example, C1, C2, C3, etc., and water as well. So we're going to have several components. So sometimes we write the equations in terms of the number of components we have, because we want to model the movement of these components into the reservoir. And as we're going to see later in the equations, for example, the C1 components, which is a hydrocarbon C1, can be in the gas phase, here, or can be in the oil phase, right? Depending on the temperature and pressure, It can be in the oil phase or the gas phase. So we want to mimic this behavior. If we have a light oil like we have in pre-salt, and this movement is behavior have to be modeled in detail. David is asking here the difference between the components and the phases. Okay, the phases, that's a very good question, David, because in the petroleum area, we have a confusion. I don't like this confusion, but I'm following this nomenclature because all the books are like this, all the papers are like this. I would do differently, but the phases are liquid, gas, liquid, hydrocarbon, gas, and water, right? These are the phases. And the components are C1, C2, C3, and so on, or even CO2, or even water. These are the components, right? So these are the difference between the phases and the components. So the petroleum can be, if you go into a laboratory, we can go into some experiments to know how much of C1 we have, how much of C2 we have, C3, and so on. CO2 and water, we can make a sample of the petroleum we have in the reservoir, can go into the labs and see how much water we have, how much CO2 we have, how much each of the hydrocarbon components we have, okay? And the phases are liquid, gas, and water, okay? In the petroleum area, we call this liquid oil, and we call this gas phase gas and water, okay? So that's normal, okay? We're just changing liquid to oil, gas, and water. What is confusing is when you're going to see the black oil model, where the components are the light component, where they call gas, the heavy component that they call liquid, and the water component they call. So the name of the phases and the components are the same. And this is a little bit confusing for those who are seeing this for the first time. But I'm trying to emphasize this when we go through the equations, okay? Is this clear, David, for you? Okay. Okay, so one of the most important things to select what type of simulator model we are going to use is the fluid. Okay, so we are going to detail a little bit, but normally we have three types of simulator, which is the black oil simulator, where we have three components and three phases, which is used for most of the reservoirs, and it's very useful for models where the thermodynamics is not so important, and this change of the components and the phase is not so important. We are going to explain why. The second type that's very important is the compositional model, where we try to write the equations by trying to separate the components, so trying to see how much of each component is moving in the reservoir. This second type is called compositional model, as you're going to see. And there is a third type related to the fluid behavior, which is called thermal models, where the temperature model. So for black oil and compositional, we consider the temperature is constant. Even though if the temperature changes a little bit, it doesn't change too much to change the fluid movements, okay? And the thermal components, no, the thermal component is used in reservoir where we are injecting vapor, where we're injecting hot water, where we are doing combustion in situ and so on, where we have difference in temperature, and the difference in temperature is very high. And as the difference in temperature is very high, we have to consider this in the fluid behavior, okay? I'm not gonna talk about the thermal models here in this course, because in Brazil, this is not so important as it is in Canada, in Venezuela, and other countries. I'm going to talk more about the black oil model because it's very simpler. The equations are much simpler and it's easier to show you, as most of the students are beginners. The black oil model is much easier to understand. It's the model you are using, for example, in the IMAX in your projects. And I'm going to give you some hints about the compositional model only, that nowadays it's important in the pre-salt, but they are very complex. So instead of spending too much time and just give you some hints about the compositional model, because the equations are very similar to the black oils. And then, of course, if you want to work with the compositional models, you are going to have to study more about this in more in different courses, okay, or by yourself. But we are going to concentrate in the black oil. But the fluid behavior is one of the most important parts for us to decide which type of computer model we're going to use. Okay. The second type of properties we have to, of course, the first one, the fluid, and the second one is the rock type. Okay. So normally we have conventional simulators, like the one we have shown here, where each block is representing a porous media, and we have a single porous media here. Of course, we can change a little bit of the properties as we have seen here in the properties. But if it's a single, if it's a single porous media, for example, if you have a block like this, if you have a block that's representing this part of reservoir, in a single porous media, I'm trying to represent the property of this block as an average of the block. For example, if I want to take porosity here, the porosity of this block is the average porosity in this block. The permeability here, for example, the horizontal permeability here is the average permeability of this block, and so on. When we have a single media porosity, we call that conventional. Just a second, David. I'll answer in a minute. In a minute. So when we are changing the porosity, for example, if the model is so complex that we have fractures and vugs and cars, representing 50 meters block by a single value is not a good idea, right? So in these situations, we can have this, what we call dual or dual pore or dual porosity media or dual permeability media. Sometimes today we have even a triple porosity, triple permeability media, and so on, where we try to simulate the matrix in some equations and the fractures, for example, or the cars in other equations. And these equations connect each other, right? When we have this behavior, we have a difference and non-conventional model. So this normally we call a single porosity reservoir or conventional reservoir. And here we call a dual porosity, dual permeability, or triple permeability, and so on. So the second aspect that we have to consider is the rock type, okay? So by here, we select the type of fluid behavior, and here by the type of equations we're gonna write for each block, if it's a fracture, of a matrix, and so on, okay? We have a question about this first, the first part. Dave, sometimes we have a solid phase in the reservoir, for example, especially close to wells, where we have a very high flux, right? Sometimes we have a phase, but in the conventional simulation models, we don't have solid phase, right? If you have solid phase, for example, in close to a well, and you want to simulate this solid movement in the reservoir, you cannot use IMAX or JAM or Eclipse, which are the simulations we are selecting. Then you need special equations, other simulators, other type of mathematical equations, okay? It was clear, David? So for us, for reservoir simulation models, we are concerned about liquid and gas, and liquid movement and gas movement and water movement, not about solid movement. If we have solid movement, especially close to wells where you're gonna, then we have to go into other equations, and we are not dealing with this in our course, okay? But this is not very important for the management of the wells. Sometimes this solid movement is important for simulating the productivity of the wells. So we may have special well models in order to incorporate the reservoir simulations, okay? Okay, Ramin is asking about supercritical conditions, so which phase we have to consider in these situations. I'm going to talk about that, Ramin. One, I'm going to talk about the phases here, just giving you some hints. We're going to explain you probably 2 classes from today about the thermodynamics of the process. But also we're gonna see this very fast here in our course. If you want to understand really about what's supercritical conditions and thermodynamics and so on, you have to take the reservoir engineering classes or thermodynamic classes, because then they will explain you much more than we will explain here in our course, okay? But the supercritical conditions or even the other conditions are related to the phase envelope that we have in the reservoir, okay? And the conditions that we have in the, let's take here. If you emulate the envelope phase here, I don't know if you have an envelope here. If the fluid behavior is a function of pressure and temperature, okay? So if you change temperature and pressure in the reservoir, we're gonna change the conditions of the well. So we're gonna, probably the engineers took these classes in the thermodynamic classes, especially chemical engineering or chemistry and so on, but even mechanical engineering and so on. The thermodynamic of the process will try to represent the fluid behavior of this. So sometimes we have, for example, the phase envelope here, where we have liquid but vapor here, and we have liquid and non-phase, and I have vapor here and liquid here. And for example, sometimes the reservoir is in this condition of pressure and temperature. And as we decrease pressure in the reservoir, we can go into this phase here where, for example, we have only oil in the reservoir, and sometimes as we decrease pressure around the wells, we go into the liquid plus phase, so we have gas inside here. So we have to understand this in compositional models. So we have to model this, is the pressure is decreasing, how the phases are behaving. So this is very important for us to model. And the supercritical sometimes is because we have here the critical point where we change these conditions from the reservoir. If you are around this area here, the behavior of the fluid there is very complex. And sometimes we have some fluids, for example, that is vapor in the reservoir, then we go into here's the two-phase envelope, then we go again to the vapor. If we are close to here, sometimes we have a clear situation where we have oil and gas. When we get close to these critical points, the fluid is not really a liquid or not really a gas. Is a fluid that have properties that are something in between fluids. So the behavior is very complex. And so when we are in these conditions, we have to have a special thermodynamics treatment, okay? That's when we call supercritical conditions, and we are above the critical point, okay? David is asking about the solid movement. Yes, David, the solid movement also can be considered in the equations if this is important for your problem. But for us, this is not a problem. So if the solid is important for your problem, we are gonna write the equations not only for the components, but also for the rock, okay? So the solid phase. So for us, this is not important. The most important part of the solid movement in the reservoir for us is if it's happened close to the well, and here, for example, you have a porous media, and the porous media has a porosity, and if the solid movement is moving through the well and it's getting here and it's changing porosity and changing permeability, then this is important for us for reservoir simulations. But instead of putting this solid movement in the equations, we can write this in the well equations, okay? I don't know why you're so concerned about solid movement, but for us, this is not important, okay? Especially for the reservoir reservoir engineering aspects of the problem. We are not talking about solid movement. Maybe solid movement is more important for the production engineers and close the wells where we change the productivity and injectivity of the wells, okay? But we are not talking too much about that, okay? Okay, so we talk about phases. Where's the mouse here? Just 1 second. We are talking about phases, we are talking about rocks. And the other important aspects that we have to consider is the displacement we have in the rock, the recovery mechanism we are gonna have. Sometimes we have a simple reservoir. We have only oil and water in the reservoir, but sometimes we are injecting CO2 or injecting polymers or injecting vapor, so on, or we have a gas coning or we have a thermal component. So depending how we're going to recover the oil, how we're going to use the recovery mechanism of the oil, sometimes we have to consider that to select the reservoir simulation models, okay? So if it's a very simple reservoir, like the one we talk here, a black oil reservoir, and we are only injecting water and displacing water by increasing pressure and displacing oil by this, then we can use a very simple simulation model, okay? But on the other hand, if you're gonna injecting CO2, is this we have a light oil, if the pressure will change a lot, if you have a model with fractures and bugs and carts and so on, then we're gonna have to use a very complex simulation model. What's the difference between this? We're going to show in the equations in the today and next class, probably in the 3 class from now, trying to explain the difference in the model when we have these different aspects, okay? And of course, if it's a simple model, the model will run in minutes. If you're a very complex model and want to represent the fractures and the carts and bugs and want to represent all the components and all the recovery mechanisms that we have, then probably you're going to have millions of blocks and the equations will be very complex. Instead of 3 equations for each block, we're going to have 10 equations each block and so on. So instead of running in minutes, we're going to run the simulation in hours or even days. So that's why it's important. If you're going to use these reservoir simulation models to optimize production, for example, as you are doing in your projects, or to improve the models in data simulation process, and are going to run thousands of simulations, that makes a big difference, okay? So here is the physical aspects of the process, and here are the choices we are going to do for this. For first choice we're going to have is the grids. So we are going to have to select the grid for our model. So we can use different types of grids. We're going to talk about regular grids, grids that are not so regular, corner point grids that are very complex grids trying to mimic the geology of the fields. We can use Cartesian grids, cylindrical grids, local refinements, grids that have hybrid grids that they are different in different parts of the reservoir. We can use Voronoi grids. It's more or less the same as corner point. Here we're going to talk a little bit about this. They have more or less the same thing, but we are going to talk more about the corner point because it's much more used in the commercial simulators, okay? Once we select the best grid for our problem, we try to considering these aspects, we're going to select the number of layers we're going to use and the number of blocks in the horizontal directions, okay? Why in this order? First, we select the grid, then the layers, then the blocks, because the grid, we'll try to consider all these aspects here. If we're going to use a more simple grid or more complex grid. Then we're going to select the number of layers because we want to see if our displacement will be important in the vertical directions, and if this will be important in the horizontal directions, and that's why we normally select first the number of layers, trying to represent better the geology and the physical mechanisms of the displacement. And then we select the number of blocks considering the maximum amount of blocks we want for the model. For example, if you have a very powerful machine and we can have 1 billion blocks, then we can have a model that has 10 meters in the horizontal direction, for example. If not, maybe 100 meters, 50 meters, 200 meters, and so on. Okay, once we have selected the type of grids and the number of blocks we're going to have, we have to select how we're going to solve the equations. I'm going to show you in the next classes that we can solve all the equations at the same time, that we call implicit models. We're going to solve all the equations, all the variables at the same time. Or you can use some models that are, for example, this is just a name, that implicit in pressure and explicit in saturation, where we are going to solve the pressure equations implicitly. So if you have, for example, 3 equations and 3 components to solve, instead of, if you have 1 million blocks, instead of solving 3 million equations, we're going to solve just 1 million equations, which is much faster. And then after we solve for pressure equations, then we solve for saturation equations explicit. Of course, and this is fast. Normally, this is faster than implicit models because we have less equations to solve. But also, we have some problems related to this. We are going to explain it a little bit because the saturation equations are not so precise sometimes. And sometimes we have some problems about this. So if normally the implicit equations are more used because they are more reliable, okay? But we are going to talk a little bit about implicit equations. And especially, we are going to talk about a method called adaptative implicit method that I recommend for you to use in all the models you're going to use in your life, because it's a method that commercial simulators develop, it's a special design for the blocks where the conditions allows. It uses explicit equations, and for the blocks where the conditions don't allow, then they use implicit equations. So before it solves the equations, it goes into the conditions of the reservoir, and the simulations automatically selects which blocks we are going to solve implicitly and which blocks are going to solve explicitly. So as you may guess at this point, but we are going to show you, this is a good method because you have a combination of the best computational time of the implicit method combined with the best reliability of the implicit methods, but only in the blocks where we need the implicit equations, okay? So I recommend you to use this all the time. We're going to talk a lot of things in this course that have advantages and disadvantages, and some of the things like this IM method, I don't see any disadvantages in using because it's very powerful. It improves a lot the simulation, the computational time of the models, and the precision is always the same as this implicit method. Okay, but don't be. We are going to talk about this method when we talk about the equations. Okay. So once we select this, and for this, I recommend you to use this IM method. We have to select the well modeling, how we're going to model the well in the reservoir. As we're going to see, the model normally is a boundary conditions for the reservoir, and we are model the wells as boundary conditions. Then we have to select how we're going to model the aquifer, which is very important. We can model the aquifer the same way we model the reservoir. Let's assume, for example, we have a very big aquifer here, right? So we can model the aquifer by selecting the movement of water in these blocks, and we can also discretize this aquifer here in numerical techniques, like doing like this. Or we can model the aquifer by using special equations that trying to model this aquifer analytically, because the important part, for example, of the aquifer here is just to throw water into this oil zone here. So instead of modeling, when the aquifer is very big, instead of adding much more blocks and much more equations in our problem, we can solve this aquifer in a different way. We're gonna see how to do it. And it's like almost like a boundary conditions for the reservoir. And for example, we are injecting water here from the aquifer to the blocks. But instead of having blocks here, we have almost a big block here with pressure and conditions that mimic the behavior of this water movement into the reservoir, okay? And this also makes the reservoir models much faster than if, for example, we have big aquifer. For example, if you have like 100,000 blocks here, we would have more 100,000 blocks here. Instead of having 200,000 blocks, we have just 100,000 and an analytical aquifer, okay? And so on. So sometimes we have to do other choices, but these are the most important choices you have to do. Okay. Any other questions so far about the type of simulators we have? Okay, once we have this, we have to consider the objective of the study. We have to physical process we are modeling, the complexity of the problem, the quality we want for this, the quality and amount of production data we have. Sometimes we have a reservoir that's using very green field, or very beginning of the life. We don't have any data. We just have data sometimes of one well and a little bit of seismic and so on. So instead of running a very complex model with 1 billion cells, and we have a lot of uncertainties, sometimes we write less complex models. We know that we have some error in these models, but we know that we have approximate solutions anyways, because we have a lot of uncertainties. So that we have to consider also the quality of and the amount of production data we have in this decision. Okay, the accuracy and the time and cost. So we have to consider all this when we are selecting the reservoir simulation models. Nowadays, one thing that's very important also, that we can change the simulation models very often. For example, considering a life of the field, in the beginning, we have a field, for example, of one well. And then after some time, we have 10 wells. And after more, sometimes 20 wells. Then we're going to run into 20 years running these 20 wells, change a little bit the wells here. So in the beginning of the life of the field, we have a lot of uncertainties, a lot of questions, a lot of things. We can have models that are simpler, okay? As we go along, we have more wells, more data, more dynamic data, sometimes seismic 4D, and so on. We keep going here, we acquire more information for after 1, 2, 3, 4 years of production, we can have much more precise models. So nowadays, it's very easy to change these models as we go into this life of the field, okay? As we can build our reservoir simulation models in Petroleum, for example, with all the geology, all the geoscience data there, the lab data there. So we keep changing the model as we need, as we go into the life of the field, advancing time here, okay? A few years ago, it was almost impossible to do that, because normally we used to take like 3-4 months to build a reservoir simulation model. If after 1 year we want to change the reservoir simulation model, we would have to do everything again. It was almost impossible to do that. But nowadays, it's very common, and I really recommend you to build all the information in a Petroleum model or MSR or any other geoscience model, because as you go along, as the months and years go by, it's very often that we have to rebuild all the model, because we have much more information and less uncertainties as we go along, okay? Okay, the number of simulations function and limitations are a function of number of blocks and number of components, of course, because the components will represent the fluids and the blocks will represent the rocks. So if you have less blocks and less components, we have less limitation and less precise answers, okay? And the information, of course, is about production, about lab and geology, geophysics, seismic, and well tests, and so on. This is information. As we have more information, as we go in time here, it's important for us to build models that are more smaller blocks with more components and so on, okay? Okay, this is just a repetition. I thought about this already. Let me see if there is any other thing. But if you have any questions, let me know. So in order to build these models, we go into these aspects that we have seen in the beginning: physical model, mathematical model, numerical model, and computational model. So the physical model has to represent all the characteristics of the block and fluids, the recovery mechanism. We have to understand what is causing the fluid movement in order to input this physical behavior in the mass conservation equations, the energy equation, if you have thermal equations, and also the movement, it's not quantity, in the flow equation here, right? The translation here was not so good. Once we have this, we have to choose the model, the number of components, and so on, as we have seen in the previous slides. So we are considering all these aspects in the mathematical model of the problems, that the equations that will represent these physical aspects. Once we have these equations, we are going to discretize these equations because the reservoirs are very complex, with boundary conditions that are complex and so on. Otherwise, we could solve these mathematical equations analytically. Of course, if you are representing, for example, a flow in porous media in a lab, that is a 1D displacement in a laboratory, for example, maybe you can solve these equations analytically, right? But if you are representing a complex reservoir like this one, it's impossible to solve this analytically. So we go into these numerical models. We try to discretize these equations considering these grid conditions here that we consider, right? And then we select the grid, the type of aquifer, the treatment, and so on. See if it's implicit, explicit, and so on, as we have seen. Then we select the boundary conditions, again here in Portuguese, boundary conditions and initial conditions here, which are the conditions that we are going to use in these boundaries here of the reservoir. Sometimes these boundaries here, and also the boundaries considering the wells. So we have these boundary conditions. We are going to input also the initial conditions, which are how was the reservoir and the fluids, how were the fluids in the reservoir in the beginning before we have any wells or any difference in pressure. These are the initial conditions, okay? We have to, in order to model to be good, we have to have good initial conditions and good boundary conditions, okay? Once we do that, we're going to select the way we're going to use the numerical models. We are not going to this aspect here in this course. There are several ways to do it. Finite difference, finite elements methods, contour elements methods, flow lines, other numerical methods like streamlines that we use here is more streamlines. More streamlines about this. All these methods have numerical errors, of course, because we are discretizing this blocking in blocks or in points or contour element math, boundary elements math, and so on. There are several numerical methods. We are not going into these numerical methods too deep in this course. I'm going to show just a little bit of the aspects of the most common we have in the commercial simulators today, which is the finite difference methods. And I'm going to show the equations using this method, but of course we can use any other methods you prefer to write a simulation code. Okay. Sorry, just a second. Okay. What normally we do in the simulation methods? Again, we are not going too deep in the equations here. We could spend one course, an entire course, just showing the equations of reservoir simulation, because there are a lot of details in how we solve these equations. I'm going to show just the general aspects of the equations here, but what we're trying to do is something very simple, that we are trying to write the mathematical equation by approximating this equation by linear equations. For example, if you want to simulate the mass movement from one block 1 to the block 2 here, we are going to try to write equations that govern these physical aspects of the movement. For example, if block 1 has a pressure that is higher than block 2, right? This difference in pressure will make the fluid move from block 1 to block 2. We are trying to write the equation that try to emulate this behavior, and then we're going to try to solve this equation, okay? In order to solve this equation, we are going to linearize this problem. For example, if this equation is something like this, and we want to find a solution about this, we are going to use finite difference methods or finite element methods or any other method that you prefer to find the solutions, okay? And I'm just giving the equations here to give you an idea on how we're going to solve. So we are going to try to represent, for example, the pressure of the blocks by approximating the pressure by a linear equation, where the pressure in neighbor P2, for example, is a function of P1 and a function of the distance between P2 and P1, for example, x, delta x, 1, 2, for example, which is this example, and the difference in pressure between the two blocks, okay? So if you represent the difference in pressure between the two blocks by these equations here, we try to represent how much are going to change the pressure in the reservoir and how much this difference in pressure will change the saturations and so on. But once we do this, we are saying that this element is R0, these elements are 0. So what we are doing, we are trying to represent the equations by linear equations because they are easy to solve. Yeah, let's write here. I'm trying to represent this by a linear equation, right? We're going to use some elements and try to represent this by a linear equation, trying to say that these elements that are non-linear here are 0, okay? So we are approximating the solutions by linear solutions. And once we do this, we have some errors related to the discretization of the problems. And these discretization errors are very important in these numerical techniques that we are using. We are not talking too much about them, but we are just talking that these are important for us because our blocks, as I told you, 50 meters, 100 meters, and so on. And we are trying to discretize this problem. And of course, if you have an equation that is like this, for example, how the pressure is changing in the reservoir, if from here to here we have 50 meters, saying that this is a linear is approximation. If the block has 1 meter, of course, this is much similar to a linear than 50 meters, right? So if you are decreasing the size of the blocks or the size of the discretization we are using, the linear approximation is okay. But if you are increasing the size of approximation, if you have errors that are related to the size of the block, the errors will be as big as the size of the blocks, or sometimes bigger, okay? So that's why it's very important for us to use smaller blocks. If the blocks are small, the error will be small, the solutions will be much closer to the real behavior of the flowing porous media. If the blocks are big, the errors are big, so we have to consider that in our solution, okay? So I'm not explaining too much in detail this equation, this thing, because it's not our focus here. We have a reservoir simulation too in our course. Sometimes we have this course because not too many students are interested in developing a simulation code. They are more interested in know how to use the simulators in the real life for the reservoir engineering aspects. So that's why we don't go in very deep in the equations here. If you are interested in going very deep in the equations, then you have to take reservoir simulation too, okay? But what we are doing here is just important thing that we are approximating our solutions by linear solutions. And by doing that, we have discretization errors. This is the most important part that you have to understand. And if, of course, if you are interested in go deeper into this, there are a lot of materials in the books that I recommend and in the papers and so on that show how these discretization errors are related to each type of grid, each size of grids, and so on. Okay, we are not very concerned about this. The only thing that we're gonna give you are some hints and how to select the grids concerning the type of problems we have, okay? And important, of course, is that if the grid is too big, the size of the block is too big, the discretization will be higher. So we need to consider this in our solution, okay? So we are not going too deep in this discretization part, okay, of course. Of course, we have to consider all the reservoir description in this problem. We have a lot of information by seismic, maps, logins, and well tests, deposition systems, similar reservoirs, outcrop systems, and so on. We can collect samples of the reservoir. You can go into the laboratory. Here is wrong. I asked a student to help me with the translation, but some terms here are not right. I'm going to correct this before I send you this, okay? But you have to represent the porosity, the permeability, capillary pressure, relative permeability, compressibility, and so on, several aspects of the reservoir. We're going to make a complete list in the next classes. And also the PVT analysis that represent the fluid behavior, okay? Or the thermodynamic equations that represent the fluid behavior, depending on type of simulator we are writing, okay? So one important aspect of this, again, is that we are trying to simulate something that is happening in this scale, in a porous media, and sometimes we are using blocks that have, I wouldn't say kilometers here, but at least 100 meters here, right? Today is an average of 100 meters is a good size, a good approximation of blocks, okay? Like I would say 100 meters would be better. In the past, we used blocks of 1 kilometer, but today it's not so common, okay? And as we go along in this process of collecting data here, we have data that has the scale of centimeters. For example, the samples here that we have from the reservoir. We have logging here that we have information about meters. We have seismic that have information about 1 to 10 to 50 meters, for example, here. The blocks have in vertical direction meters and the horizontal directions 100 meters. We have some information about dynamic data, for example, well tests that represents up to kilometers here. And then we have to put all this information in this reservoir simulation model that have kilometers, but we have to put all this information in this to represent. So it's a very complex problem, as Manuel told you in his seminar. I don't know how many of you have done this before, but this is very complex, so we have to consider all these aspects into the reservoir simulation model. That's why normally we have multiple reservoir simulation models and we consider uncertainties in this process, okay? Those uncertainties that we have to consider, as we have shown you in the 12 steps methodology, in the closed loop methodology, as Celio showed in the data simulation, so on, we put a lot of uncertainties, not only in the properties of the block, on the behavior of the fluid, also in the numerical model and so on. And as we have dynamic data, we mitigate these uncertainties, decrease the uncertainties in order to have more reliable production forecasts, okay? One part that's very important here I want to emphasize is that we call transferência de escala in Portuguese, right, at upscaling. Once we do all this change in these scales to the reservoir simulation model, and we select the grid size, we have to upscale all this information, for example, that we have seen here. If you have here this reservoir simulation block that has these meters and 100 meters here, we have to change all this information in this scale to this scale of the reservoir simulation model. And this is not an easy task. I'm going to show you some examples. An example very, very simple, for example, here. Let's assume that we are displacing water, displacing oil here. And I have a simulation here of 100 meters, for example. And I have a fault here, okay? I cannot, for example, use a simple average of this, of porosity and permeability, for example. Why? Because if this is a very exaggerated example, but just to give an example why we have to be very careful. For example, if you have water displacing oil here and you have a sealing fault here, the movement here is zero, right? So when we write the equations here, if you write the equations trying to represent this, and we take the average porosity and average permeability, the average porosity and permeability of this block is not zero, right? If you use a just simple arithmetic average, for example, So when we are trying to simulate this, we are going to simulate here as an average permeability and average porosity, and we are going to have flow from this block here, 1, 2, 3, for example, from block 1 to block 3. We're going to have flow from 1 to 3. But if you have this sealing fault here, and the sealing fault don't allow the fluid movement, then our average porosity in the horizontal part here should be 0. I have to find a way of upscaling that the horizontal permeability here is 0. Maybe if I have a higher pressure here, maybe the fluid can go up and down, but not horizontally here, right? So this is very important when we consider these upscaling techniques, because we have a very heterogeneous media. We have faults, we have barriers, we have cars and vugs, and faults that are not sealing faults. We can have faults where we have fluid movement and so on. So we have to consider all this. So these upscaling techniques are very important for have good models, okay? The other aspects I think I have told you already. Again, we have a very thin grid, or if we say thin grid is like this direction, Z direction, the vertical direction here is very different from the horizontal directions here. And they have reservoirs normally that are very thin, but as we have seen, and I have told you, we are discretizing the vertical direction very different from the horizontal direction, okay? This is, so we need special techniques to upscaling this type of reservoir, as we're gonna see in the course, right? And normally to do that, these upscaling techniques, we also combine this with geostatistics. I don't know how much you guys heard about geostatistics, but these are techniques that we have inside Petroleum, inside RMS or other geological software that we can use to represent the rock behavior in the well, okay? How we're gonna do this. So Manuel told you about this. I'm not gonna repeat this, okay? So we can have blocks that go today up to almost 1 billion blocks. We have some reservoirs running in the world that have more than 1 billion blocks. But normally the simulation here for typical real reservoirs that we have, maybe it's going from 50,000 to 1 million blocks would be a good size of reservoir we are talking about. So if we are using a black oil model in 3 equations, for example, we are running here 3 million equations would be a good approximation of a very fine model. And here, a good approximation for a model that is what we call low fidelity model, as Avanci told you, okay? Okay, the upscaling, what we are talking about is this, for example, assume that this black part here is the reservoir simulation block. Let's assume that a very high fidelity model, as we call, as Avanti told you, a very fine model, come from geology, has this aspect here, for example, of this fine block. And our reservoir simulation model is this one in black here, okay? Let's assume that we want to represent the properties of this coarse block, considering all this fine scale that I have represented from geology. So what I need to do is to represent this into this, okay? So I know that I have all these properties. Let's assume, for example, that this color here is porosity. It can be porosity, permeability, vertical permeability, horizontal, or any other aspect related to the rock type, right? Let's assume that I want to represent this. So I have to represent an average property here. For example, if this is porosity, each block has a different porosity, and I have to represent here's an average porosity here. Let's assume that this is a permeability. I have to represent here X permeability and Y permeability here. So I have to take all this information from a fine scale in geology and a high fidelity model, for example, representing each 5 meters or each 10 meters and so on, and translating this into a block that has a 50 meters or 100 meters. And then I want to have a model that the flow through this blocks here has the same behavior as the flow to this block here. As you may guess at this point, the flow at the right part here in this block will be an approximation of the other. And we have to use special techniques in order to mitigate these problems, okay? So the upscaling techniques are very important for us to build models that are reliable, okay? I'm gonna talk more about this upscaling technique, but of course we will not be enough because it's a very complex subject. If you are interested in this, there are a lot of books and a lot of papers and so on talking about these upscaling techniques. And there are a lot of options in Petroleum and RS to do these upscaling techniques. So you don't have to learn details on how to build these techniques, but how to use these techniques, okay? There are some techniques that are very simple, just an average, for example. Then there are several techniques that are more complex average of this. I'm going to talk a little bit about this. And there is also some numerical techniques that are used to use here. I'm going to talk a little bit more about these numerical techniques, but Petrel, for example, can use a numerical technique to translate this property to these properties. How it does? It put boundary conditions here. It imposes a flux here from here to here. It do a numerical simulation of these blocks here, or these 6x6 blocks, and then it calculates the average porosity that has an equivalent flow from these 6x6 blocks, and then use these average properties into our reservoir simulation model. Of course, this is a little bit more precise than using a block. For example, if I was in that case that has a barrier here, of course, I would have a vertical permeability here, but not a horizontal permeability here, or a Y permeability, not a X permeability. So this numerical model would be able to emulate all these aspects. But of course, if I do this numerically, I would have to take block by block in the course block, go into a simulator, simulate all these conditions. It takes a long time. If I have a very complex reservoir, it takes like hours or days to do these numerical techniques in a very complex reservoir. So again, everything that we do that improves a little bit the quality of the model, normally we have to wait time to do that. And sometimes, especially in companies, we don't have unlimited time to do all this. Maybe you can ask, but this is, I'm gonna do just once, and but imagine you are doing a data simulation process where we are changing these images all the time, and we have 100 models, as Celio showed you, and I have to do these upscaling techniques. Every time I do adjust statistic techniques to update the properties, I have to run these upscaling techniques again, and this takes 1 day to run. That is a lot of time. And so we have to consider this in the type of solutions we are doing, okay? Okay, these are, I've seen already. These are the simulations we have. I'm not talking too much about this. You are using in the project the IMAX. For the pre-salt, we are going to talk a little bit about the GEM, which are the compositional models. The thermal simulations, for example, for CMG, is the stars. We have the equivalent, the black oil, compositional thermal. We have from scene, which is a 3DSL, which are streamline simulators that we are not talking too much because they are not very used nowadays. We have Nexus from Halliburton and other components, and we have several commercial simulators that can use. We are concentrating the analysis in our course using the IMAX one, okay? Why? Because it's the simpler one to use. The black oil is the simple model, and IMAX is a simpler model to use. And once you understand what is basically inside the reservoir simulation equation, the rest is not so complex to learn by yourself, okay? Of course, you can take other courses and improve your knowledge in how the compositional simulation works, how the thermal simulation works, how the streamline simulation works, and so on. But it's not impossible for you, if you know black oil models, how to move from black oil to the other simulations, not so complex. Okay. Okay. Here I'm going to talk a little bit about the Cartesian grid aspects of the process. Maybe we can have a break. Now it's 15 to 10. We can make a break in 15 minutes, 10 minutes, okay? Because we're going to have to stop in an hour from now. Maybe 10 minutes break, 5 minutes before 10 o'clock, we come back, okay? Just interrupt